Good afternoon, everyone. I think we could go. Good evening. I think we can start. So we continue our series of workshops with about wireless communications, and today we'll have a talk by Vyacheslav Loginov, who will present his latest results related to collision resolution methods for LT, LAA, or NRU base stations coexistence with Wi-Fi networks in a licensed frequency band. And as previously announced, so we'll have about 40 minutes. So the talk will be about 40 minutes, and it's up to the speaker whether to allow questions during the talk or to postpone them till the end. So what I propose is that we have here a chart. So if somebody has questions during the talk, I propose to write down the questions in the chart, or to just raise your hand, or write letter Q, means question. And when the speaker will have, when the speaker makes some pause, so he will address these questions, and so I think it will be more easier to proceed. So let's start. Slava, the floor is yours.
Evgeny, thank you for your introduction. So let me start. As Evgeny said, my presentation will last about 40 minutes. In my talk, I will give you some introduction into the coexistence of Wi-Fi and cellular networks in unlicensed bands. In particular, I will compare channel access methods in Wi-Fi and cellular networks, which they use for unlicensed bands. After that, I will go to the mathematical models of coexistence of Wi-Fi and NRU. In particular, I will start from Wi-Fi only scenario, which is a classic scenario. And then I will go for coexistence scenario, Wi-Fi and NRU, and consider both baseline solution and solution that we have proposed. And then I will finish with the numerical results we obtain with the developed models. Nowadays, mobile data traffic is growing each year. According to the reports from Cisco company, a volume of traffic is growing continuously every year. But do current cellular networks have enough capacity to serve such amount of traffic? Let me turn to the upper limit of network capacity which can be achieved. According to the classic theorem proved by Shannon and Hartley, channel capacity C equals channel bandwidth multiplied by the logarithm of signal to noise ratio. But how much channel bandwidth B do cellular networks have? Okay, in theory, according to the 3GPP specifications, initial releases of 4G and LTE networks have only 20 megahertz of channel bandwidth. However, in 2016, cellular base stations was able to use up to 640 megahertz of spectrum. However, in practice, close the chat now. In practice, the network operators use much less channel bandwidth. For example, in Germany in 2017, there was 3 telecom operators, and none of them use more than 50 megahertz of spectrum. So why does it happen? It happened because legacy cellular networks use licensed frequency bands for transmissions. On the one hand, with license or on a frequency band, cellular operator has an exclusive permission to transmit in the band. And cellular base station is able to control all the transmissions in the band. On the other hand, operators have to pay for license, and the price is very high. Also, license bands have very limited bandwidth. So what about unlicensed spectrum? For example, there are more than 400 megahertz of spectrum is available, depending on the country, in the 5 gigahertz diapason. This spectrum is free. You don't need a license to use this spectrum. However, there is some drawbacks. For example, to use the spectrum, you need to satisfy local regulatory requirements. For example, you have to use listen before talk technique, which I describe later, and you have to you cannot exceed maximal transmission power defined in regulatory requirements. And also, if cellular network uses unlicensed spectrum, it have to coexist with other technologies. 3GPP has recently developed LTE-LA and NRU technologies that allow cellular base station or GNB to use these unlicensed frequency bands for transmission. Let me turn to the comparison of channel access methods in Wi-Fi and cellular networks. Let me start from the implementation of listen before talk in Wi-Fi. Having received a packet from the upper layer, a station has to wait until the channel becomes clear. After that, it initializes backoff counter with a number distributed uniformly in the interval between 0 and current contention window. The station decrements backoff counter if the channel is sensed idle for slot duration sigma. If the channel is sensed busy, Wi-Fi station suspends backoff counting until the channel becomes free again for special interframe space. After that, when the channel becomes idle, the station resumes backoff counting. When the backoff counter reaches 0, the station starts data transmission, which is followed by the receiver station sends back an acknowledgement if the transmitted data packet is received successfully. If acknowledgement is not received during a special acknowledgement timeout, the station decides that the packet was lost and retransmission is needed, and then it increases contention window and repeats the backoff procedure again. Obviously, collisions in Wi-Fi are inevitable. To reduce negative influence of collisions, Wi-Fi station may use RTS-CTS frame handshake prior to data transmission. In particular, station, after finishing the backoff procedure, it sends not the data, but special short RTS frame. Having received RTS, the receiving station sends special, again, short CTS frame. Only having received CTS frame, the initiation station sends data packet. This RTS-CTS mechanism, as a result, slightly increases successful transmission duration, but significantly decrease the collision duration, since only short RTS frame are collided if this mechanism is used. In general, listen before talk in cellular networks, LTLA and NRU networks is similar, but there is a number of differences. First, acknowledgements can be transmitted in the license channel. Second, contention window is increased only if the data is corrupted. Also, cellular networks does not have RTS-CTS mechanism or something similar to decrease negative influence of collisions. And the last difference, which I want to highlight, is that all the transmissions of cellular base stations must be synchronized with the license channel. And this leads to the fact that cellular transmission in unlicensed bands may start only at licensed channel slot boundaries. And it leads to the following problem. Let's suppose that cellular base station may start data transmission in these points, which these possible frame start positions. Let's suppose that it has finished the core procedure here. It can start transmission data transmission in unlicensed channel here. So there is a question: what should base station do in between of the end of core procedure and possible frame start? This is not covered by the cellular network specification. There is several possible solutions for this problem. The first solution is just to keep silent before the slot boundary and start data transmission if the channel is free just before the possible frame start position. This approach has several disadvantages. For example, other node may occupy the channel during this interval, and this will lead to low cellular network performance when coexisting with Wi-Fi networks, as we show in one of our previous papers. The second solution, which is used almost in all papers devoted to the LTLA and NRU networks, is to send a reservation signal which does not carry any data, any user data. This approach also have disadvantages. For example, a reservation signal itself is quite big overhead because up to 500 microseconds of airtime is wasted for transmission reservation signal. And also it may lead to asymmetric collisions, and I will talk about a bit later in more detail. And the last approach which we consider today is to use reservation signal not only for blocking other nodes, but also for collision resolution. We have proposed this approach in our recent paper, and I will talk about it today. Okay, now let's turn to the mathematical modeling. As I said, I will start from the Wi-Fi only scenario for better understanding. One of the most famous papers devoted to the mathematical modeling of Wi-Fi was presented by Professor Giuseppe Bianchi, and this paper now have more than 10,000 of citations. The key assumptions of the model presented there are listed here. First of all, we assume that there are n Wi-Fi stations in radio transmission range of each other, and there is no hidden terminals. We assume that all stations have saturated full buffer traffic. And also we consider that the channel is ideal, which means that packets are lost only because of collisions. Important assumption in the Bianchi model is that at each transmission attempt, each packet collides with constant and independent probability rho. And also, we assume that all stations use the same modulation and coding scheme and the same frame size D. But this is assumed only in this talk for simplicity. For generalization with different frame sizes, look into the original paper. So, according to the proposed approach, network operation is split into so-called virtual slots. Virtual slots is an interval between two consecutive Bykov countdowns of all the stations. They are all synchronized if the first assumption is met. In particular, Bianchi has modeled behavior of a station using Markov chain for Bykov procedure of given station, which is presented here. Chain state B sub EG is described by the Bykov stage E and current Bykov counter G of considered station. Having found stationary distribution of this chain, it's possible to count probability tau that a station transmits in a randomly chosen virtual slot. And it can be found as follows. Note that tau depends on the contention window size, which is constant usually, and probability rho, which is the probability of a collision seen by a packet being transmitted on a channel. And this probability rho can be calculated as a function of tau as this, because a collision happens if at least one more Wi-Fi station have also decided to transmit a packet in a considered virtual slot. We can solve this system of equation using numerical methods and find tau. Having found tau, it's quite easy to calculate Wi-Fi network throughput. It can be calculated if we divide average payload delivered by a network in a virtual slot. If we divide this by the average virtual slot duration. Some station successfully delivers data in a virtual slot only if it is the only station that decides to transmit, and this probability can be found here. And using tau, which we found on the previous slide, and average virtual slot duration, it also can be easily calculated using probability tau. So we find a Wi-Fi network throughput. Now let me turn to the coexistence scenario. First, let's consider baseline solution when cellular base stations use reservation signal after the Bykov procedure. Let me first describe assumptions, what we changed comparing to Wi-Fi only model. Of course, we now have two classes of stations, of nodes. So one of them is Wi-Fi stations. We assume that there is N sub W Wi-Fi stations and N sub L NRU base station GNSBs. And they are also in radio transmission range of each other. And also there is no hidden terminals. We also have probability rho for each type of stations. We also assume that all stations use the same MCS and same frame size for simplicity. And all GNSBs also have the same transmission duration. but we assume that their transmission duration is larger than the transmission duration of Wi-Fi stations, because by default, in cellular specifications and Wi-Fi transmissions, such conditions are defined. We also assume that duration or t of the interval between the end of backoff of G and B and the next starting position is distributed uniformly on the interval from 0 to theta, where theta is the period of slots in the license channel. And finally, in case of collision with Wi-Fi, we assume that uncorrupted part of NRU transmission is successfully decoded. As I said, in our model, we want to take into account asymmetric collisions. As I said, when describing LBT in cellular networks, NRU GNBs detect collisions only if the data is corrupted. If Wi-Fi transmission is shorter than reservation signal of GNB, this GNB doesn't understand that collision has happened, as shown in the picture, and almost always successfully transmits its data. The problem is more noticeable when Wi-Fi uses RTS-CTS mechanism. The duration, because the duration of RTS is small, about 40 microseconds, comparing to the reservation signal, which duration is up to 500 microseconds. So let's turn to the mathematical model. Again, we have probability. We first need to find probabilities tau and rho, but we have these probabilities for each class of stations. As for probabilities tau, they remain the same as in Wi-Fi only scenario, because they describe the backoff procedure, and the backoff procedure remains the same, and it is the same for both technologies. In contrast, probabilities rho are different. Probability for Wi-Fi, this probability for Wi-Fi can be found similar to the Wi-Fi only scenario, but for cellular network, we should take into account asymmetric collisions, which happen if at least one station transmits with a given GNB, and its duration is shorter than the duration of reservation signal. If we solve the system of equation on the previous slide, we again find probabilities tau. And Wi-Fi throughput in this case can be found quite similar to the Wi-Fi only scenario. We also find probability of successful virtual slot of Wi-Fi and average virtual slot of the system. As for cellular network throughput, it's a bit different. First, let us consider a case when Wi-Fi don't use RTS-CTS. In this case, we need to take into account that NRU delivers data not only in the not only in the case when there is no collision with other nodes, this probability, but also when there is a collision with some Wi-Fi station, and in this case, uncorrupted part of the transmission can be successfully delivered. In case when RTS-CTS is used in Wi-Fi, the throughput can be found similarly, but here we should take into account that sometimes duration of RTS is shorter than the duration of reservation signal, and RTS do not corrupt the data of cellular network. So let's now turn to the let me turn to the proposed collision detection method. We call it CR-LBT. When GNB uses the proposed method, it splits the interval between the end of backoff procedure and data starting position into collision resolution slot or CR slots. In the first part of CR slot, GNB transmits a reservation signal. In the second part of CR slot, GNB either transmit reservation signal or listen to the channel. If the channel is sensed busy, GNB detects collision and repeats the backoff procedure when the channel will become idle again. If the GNB has not detected the collision after all CR slots, it starts data transmission. How to select the durations of each part of CR slot? The first part is needed to reserve the channel. Its duration should be selected, so it should be enough for other nodes that still count in the backoff to detect that the channel become busy. And in case of we want to design the proposed method in such a way that in case of collision, the reservation signal shall affect Wi-Fi transmission as little as possible. For that, we set its duration of the first part of CR slot equal to the duration of LSTF preamble in the Wi-Fi frame. This is the first part of the Wi-Fi transmission, and it is the special sequence defined in the standard, and it has very high reliability. The second part of the CR slot is needed for detection of the collision. During this part, GNB must be able to switch from radio from transmission to receiving state to detect whether the channel is busy or not, and to switch back from receiving to transmission state. And also, this duration shall be less than the minimum interval after which another GNB or stations that is not involved in the collision may resume the backoff procedure. For example, in the Wi-Fi standard, this minimum interval equals to 25 microseconds. So as a result, total duration of CR slot delta equals approximately 30 microseconds. In our paper, we assume that in the first CR slot, GNB always listens to the channel to detect the collisions with Wi-Fi stations. In the following CR slots, GNB listens to the channel with probability C and transmit data during the second part of CR slot with probability 1 minus C. We have proved the following simple theorem, according to which we consider that n GNBs and none of Wi-Fi stations simultaneously finish the backoff procedure, and there are CR slots available for collision resolution. Then collision resolution probability can be found as follows. The next question is, what is the maximal collision resolution probability for a given number of n and GNSBs, which have collided, and k CR slots? In our paper, we have found a closed form solution for several simple cases, but for other more complicated cases, it can be found in closed form. but it can be easily found using numerical methods, for example, exhaustive search. And you can see the example for k equals to 4 in the picture. So we know which is the maximum probability for a given n and k, but how to choose xi when the network operates? In this picture, you can see optimal value of xi that maximizes collision resolution probability for given number of n and GNBs and k CR slots. And you can see that it is quite different, but it tends to the 0.5 when the number of CR slots, when we increase the number of CR slots. So we think, what if we always use this value xi equals 0.5, which is in fact optimal value for n equals 2. As you can see, if we have low number of CR slots, the usage of xi equals to 0.5 may quite significantly decrease probability of collision resolution. But again, when we increase number of CR slots, probability of collision resolution rises quite fast. So take into account that the probability of a collision involving transmission of n GNBs sharply decreases with the arrays of n. In the following experiments, we use xi equals to 0.5. So finally, let me describe the network model when the proposed collision detection method is used. Comparing to the model of baseline solution, we have added only one assumption to take the account of duration of to take into account CR-LBT design. In particular, we assume that transmission of a station can be decoded in case of collision if the following conditions are met. The first condition is that the collision involves only one Wi-Fi and at least one GNB transmissions. Also, we assume that also the second condition is that GNBs have detected Wi-Fi transmission using the proposed CR-LBT mechanism. And the last condition is that the Wi-Fi receiver successfully decodes the preamble and, as a consequence, the whole transmission, thanks to capture effect, which occurs with probability xi with probability eta in our model. So this is how we model that the interference in case of using our method, the NRU transmission interfere only with LSTF preamble, which is quite reliable. So again, we first need to find probabilities tau and rho. Again, tau are the same as in Wi-Fi only scenario. In probability rho, we take into account capture effect and that some collisions of cellular GNBs can be resolved using the proposed method. And here we also need to calculate average probability of resolution of a collision of exactly E GNBs and the averaged over the number of the available number of CR slots. Wi-Fi network throughput is again can be found similar to previous model, except for in probability of successful virtual slot, we take into account capture effect. When we found probability of NRU, it's again quite similar to the previous case, but we need to take into account that some collisions are resolved using the proposed CRLBT method. So let me turn to the numerical results. First, we validate our model using simulation. In the picture, you can see the results of the experiment when number of stations equals to the number of GNODBs and RTS-CTS mechanism is not used. In simulation, we didn't use a number of simplifying assumptions. For example, independence of the conditional probability rho of a collision from the Bykov stage and equiprobable distribution of the interval between the end of Bykov and GNODB starting position. And as you can see, relative error is below 5 or 7% in all of the considered scenario, and in most of them it's close to 0. So let's compare the performance of baseline solution and the proposed CRLBT solution in the scenario with equal number of GNODBs and stations. First of all, as you can see, these 4 curves correspond to the NRU network throughput, and NRU network throughput is almost the same with or without the proposed mechanism. Also, we can see that NRU throughput is much greater than the throughput of Wi-Fi, because by default, transmissions of NRU is much longer than transmissions of Wi-Fi. Also, we can see that Wi-Fi throughput is notably improved when CRLBT is used here. And we can see that the lowest Wi-Fi throughput is achieved when both baseline and RTS-CTS are used because of impact of asymmetric collisions. Finally, let me turn to the different scenario in which we fixed number of nodes to 10 and change the percentage of Wi-Fi stations. In the left picture, you can see the throughput gain from using the proposed mechanism comparing to the baseline mechanism. And in the right picture, you see total throughput of both networks. So, as you can see from the left picture, the proposed mechanism significantly increases the total throughput of Wi-Fi, as you can see by watching on blue and green curves. And also we can see that CRLBT allows increasing throughput of both networks if in the left part of this plot, when a number of Wi-Fi stations is less than the number of cellular base stations. So let me conclude my presentation. In our work, we have proposed a CRLBT method for cellular networks, which uses a reservation signal for resolving collisions in unlicensed bands. We have created analytical models of both baseline operation, which means that when the GNB always sends the reservation signal, and the proposed CRLBT solution to compare them performance. Also, we have shown that the proposed CRLBT method notably increases Wi-Fi throughput, and if a number of NRU GNBs is higher than the number of Wi-Fi stations, increases throughput of both networks. And we have, you can find full paper in the IEEE Transactions on Mobile Computing journal. Thank you for your attention. I will be glad to answer your questions. Okay, so could you please explain what is the cause of asymmetric collision which technologies suffer from these collisions? Okay, in fact, the main reason of these collisions is that the duration of Wi-Fi transmission may be shorter than the duration of reservation signal. And in this case, Wi-Fi have collision, but NRU network, the cellular network, doesn't have the collision. And as a result, after that, Wi-Fi station increases contention window, but NRU network decreases, and NRU base station decreases contention window. And this leads to the high asymmetry of channel resource sharing. So as we can see, as I have shown in the numerical results, in this case, the throughput of Wi-Fi network is significantly decreased. Are you satisfied with the?
Sorry, just one maybe comment. So this is the case when Wi-Fi uses RTS TTS frames. So yeah, when short RTS frames is transmitted during reservation signal, definitely we will have the collision, and Wi-Fi station will have to back off. And whether this problem arises when Wi-Fi does not use RTS TTS.
Yeah, this problem also may happen if the amount of data which Wi-Fi stations want to transmit is not big, or if it use high MCSs, and this resulting into the short Wi-Fi transmissions. So in fact, RTS-ATS, this is just example of short Wi-Fi transmissions. Yeah, the asymmetric collisions will happen if the transmission of Wi-Fi for some reason is short.
Okay, so and if the transmissions are higher than the slot duration, so this will not lead to asymmetric collisions, and in this case, let us say two technologies will coexist in fair manner, right?
I would not say that is fair. It will be fair if the duration of the transmissions itself will be equal, but by the default, the transmission durations in Wi-Fi and cellular networks are different. So I would say that when RTS-CTS
I mean used, fair in terms of the probability of accessing the channel.
This statement is correct. Yeah.
Okay.
May I comment a bit? In modern Wi-Fi, when we use aggregation and when we try to transmit a lot of data at once, there is a recommendation to use RTS-CTS. So some protection should be used. So it means that we did not run any experiments to clarify when and how RTS are sent in modern Wi-Fi, but it seems that when we transmit a lot of data, we do use RTS-CTS.
Yeah, and what our results have shown that interesting effect that imagine you understand that your throughput is low and you want to enable some protection method, which is RTS-CTS, in fact. And what you get is that your throughput will not increase, but decrease because of asymmetric collisions. So compare pink and gray curves. So asymmetric collision problem is quite important in modern Wi-Fi networks.
Thank you for the comments. Yep.
Okay, the second question is, what is the typical number of 4 CR slots? This depends on the number of period of license slots in LTE networks, which is for cellular networks of 4th generation. This period equals to 1 millisecond. So the average duration of the interval is about 500 microseconds. So typical number or average number of CR slots is something like 17, so greater than 10. In NRU networks, this license slot period can be decreased. And in fact, in our paper, we conducted some experiments to compare the performance of NRU network. But we have shown that we have found that this will not increase in general the performance of NRU. So we have found that we don't need to decrease this period, and it's better to have more CR slots for performance of cellular network. So it was quite a big answer. Hope I have answered the initial question of Ilya.
Yeah, thank you very much.
Okay, and the last question about the structure of the collision resolution slot. And
okay, let me just explain in more detail what the question is about. Could you please turn to the slides when you show some details on how you how you construct the slot. So generally this slot consists, as I understood, it consists of reservation signal. So the signal which we transmit in order to make the channel busy for other stations, so to resolve the channel actually. And the second part is sensing. And there was a consideration that let me check which one. So when you send reservation signal, it should not be so long in order to have a negative effect on the actual Wi-Fi transmission, because if it happens in the sensing interval, we will see that there was a collision. So my question is why we first transmit the same signal and then use sensing? Why not vice versa? So maybe we need first to sense the channel. For example, if we see that some station has started transmission, then we don't need to send reservation signal because we definitely know that it will lead to collision. So why not to just my simple thoughts? Why not to change these two parts? So this is just my consideration. Maybe it's
okay. Thank you for your questions. The short answer is that it doesn't change anything. The long answer is that you just by doing this, you just increase your backoff procedure by 1 slot. Why? Because maybe I haven't mentioned this, but the backoff slot is slightly higher than this and equals 9 microseconds. So in fact, if you sense first, it's similar to that you have not finished the backoff procedure. you sense the slot, and if you have not found any transmission, you start the transmission after that. Other stations will not detect your transmission because 1 microsecond is not enough to detect that the channel becomes busy. So if you start sensing and then start the transmission, you can have a collision just in the second pickoff slot. I don't know, maybe it's a bit confusing explanation, but
yeah, I get your point. So actually, yeah, if we would consider additional sensing for the G node B, yep, it will lead. Actually, you're right. It will lead just to increase of the backoff for the G node B. Just make it longer. Yep, and still the collision may happen in next slot. So yeah.
So by sending reservation signal and at the end of backup procedure, we virtually fix the number of stations which take part in a collision, if there are some stations that have a collision. So if you do not do this, in the second slot, some other stations start transmission, so it will be the same. I guess the next question from Lydia.
Thank you for your presentation. So I've spent some time searching for your work and just having a brief read of it. So I think that's a very good job, and I just wonder whether some members of producers or vendors for cellular networks showed any interest in your results, because in my opinion, coexistence of 5G technologies and Wi-Fi is something that will be abandoned, or very popular in the future, that will just appear frequently. So I wonder if there is some interest from other people in the solution.
So, in fact, I don't know. I can speak about it for quite a long time. So, in fact, we have presented the initial version of this of the proposed mechanism in the joint workshop, which was held by IEEE 802.11 and 3GPP, and the result was, I don't know, about a bit confusing, because in fact since this part is not covered by specifications, in my opinion, even if if some vendor implements such method, we cannot understand that, unfortunately. But this will improve coexistence, as we show.
Slav, if you don't mind, I will add something.
Okay.
Actually, the result of the presentation was quite interesting, because there were a lot of comments during the presentation, but sometime later Andrew Miles, who is the chair of coexisting committee within 811, and one of his main activities is discussion on the coexisting issues with 2GPP. He liked very much this proposal. He's from Cisco, and since Cisco is very interested in providing good coexistence Wi-Fi with 5G, because Cisco equipment will suffer if there were no fairness. So he escalated this proposal and tried to make a letter from 802.11 to GPP with the description, brief description of this proposal, like, please look in 802.11, we found a good solution that can solve all our issues for coexistence between 802.11 and 2GPP solutions, so it will be really a very good solution. But this letter was not supported by the group for two reasons. The first reason, maybe not for several reasons. The first reason is quite a formal reason that 802.11 develops Wi-Fi, but not cellular technologies. And that's why it's not the deal of 802.11 to recommend or to instruct GPP what to do. So they can provide some information, but they cannot instruct. The second issue is that, as Slava already said, this reservation signal is actually forbidden in Europe. It is not put into any spec, but this solution is working outside Europe. And the question is like, so if there is something behind the standard, why we need to add something to the standard to avoid the issues which occur if we use some ideas which are not in the standards. Yeah, so it's like another formal issue. The third for formal reason. The third reason was that many people, many companies that work in 802.11, they also work in 2GPP, and they sell equipment for both technologies, and definitely the market of 5G and 2GPP is much higher than Wi-Fi market, just because the equipment is much more expensive. And that's why they do not want to support some cheap technology if they can improve the devices working in 3GPP according to the 3GPP technologies, which are more expensive. So for these reasons, the letter was not supported, but anyway, the discussion, the interest from the group was very high to this proposal.
Okay, so I'll just follow my question then. If the mechanism with the reservation signal is forbidden in Europe, do you know what mechanism is used instead, or there is no information about that?
In fact, I don't. I'm not sure that it's forbidden. It's kind of gray zone of regulations, and there is much of discussion of whether the cellular base station can use reservation signal or not. So maybe some operators or some vendors use implementation with reservation signals in Europe too.
Okay, I'll just make a quick comment. So from the answer by Evgeny, it sounds like it's quite a sad story for Wi-Fi, and it seems like LTE just doesn't want, the developers of LTE do not want to listen to the proposals of IEEE, and so my question is whether the coexistence of LTE and Wi-Fi will emerge eventually. What is your opinion?
My opinion that it has to emerge, because for now, globally, the number of base stations of which use unlicensed spectrum is not high. So there is no, in practice, this problem is not huge. But every year, the number of such networks increase, and eventually we will have coexistence problems. There is a lot of discussions starting from 2015, I suppose, but between the 3GPP and IEEE 802.11, but the discussion is very hard because every part of the discussion want better for its own technology, and it's very hard to make an agreement.
Okay, let us hope for the best. Thank you, Vyacheslav. Thank you, Evgeny, for your answers.
Okay, I guess the next question should be from Mikhail.
Well, actually, while you were answering the previous one, I have answered to your question by myself, so to my question by myself. So
okay.
Never mind.
You're welcome.
For your talk.
Evgeny, you want to add something?
Yeah, I would like to comment a bit.
Okay.
So I initially I tried to comment during your answer, then I decided to make my comments in a fair manner, so within the common queue. I have several comments to what was said. So first of all, if we look into the regulation documents that describe channel access in a licensed spectrum, it is written there that the devices shall not emit some signals or some energy in the channel if this signal does not carry any data. And reservation signal is just such type of signal. So it doesn't carry any data, it doesn't transmit any data. The only purpose of the reservation signal is to make the channel busy. And that's why IEEE documents explicitly forbids such type of signaling. Of course, some vendors may develop some equipment which is not fully correspond to regulation, but okay, at least we shall try to follow the documents. So outside Europe or in the countries where IEEE documents have no power, so in these countries reservation signal can be used, and that's why this topic is very important. for example, US. Yeah. Now the question is why we need reservation signal, and unfortunately here there is a big problem, because without reservation signal, 3GPP devices cannot access the channel at all if Wi-Fi traffic is saturated. It means that why it happens, because so Wi-Fi stations can transmit once they finish the backoff procedure, but LTE stations needs to wait till the end of CR slot. And since the slot duration, not CR, but LTE slot, and since the slot duration is like half a millisecond in 5G or 1 millisecond in LTE, so this time is too long. And definitely if you have several Wi-Fi stations that contend for the channel and some LTE stations, so LTE devices, so definitely, or like very likely, Wi-Fi will win the contention. So that's why it's important. So you cannot, so we have problem that without reservation signal, we cannot obtain high performance for LA, but with reservation signal, Wi-Fi devices suffer. And the goal of our work when we invented this collision resolution procedure was to achieve fairness, because if we use reservation signal, it's very bad for Wi-Fi. If we do not use reservation signal, it's very bad for LA. So the truth is somewhere in between. So this was my comment related to regulation and related to the necessity of this procedure. Thank you.
Thank you for your comments. So just my comment that there was a lot of arguments about the, the statement that Evgeny said that nobody should not use the unlicensed channels to transmit something which is not data. But there was some position from 3GPP, from companies from the 3GPP that, in fact, reservation signal may be considered just a single byte, single bit that have started the transmission. Yes, it's very ineffective, but it can be somehow considered in this way. So it was a very long discussion, and fortunately it ends like, I guess, Evgeny said.
Yeah, it's just a cheating, and before going forward, let me add something more related to the future of this technology. So I wouldn't say right now, I wouldn't say that in legacy spectrum like 5 gigahertz, there will be a lot of issues without this fairness, because it's unlikely that we have LA stations as deployed in a similar manner as Wi-Fi stations. So for Wi-Fi networks, we definitely have much higher density, and Wi-Fi access points can be located from another, like 5 meters or 10 meters, and it's okay. For cellular networks, it's hardly possible to deploy these devices, the base stations, too frequently. and to achieve such a density of LA stations. However, if we look in the millimeter wave communications, so maybe or higher frequency, maybe some issues will arrive. So let's see.
Thank you for your comment. I guess the last question is from Artem, or maybe we, during this long discussion, we have already answered the question.
Maybe just my other comments to this very interesting discussion. So if we see that there is no interest in 3GPP, or maybe 3GPP is abstaining from cooperating, maybe Wi-Fi can do something to protect itself from these asymmetric collisions. So so what you propose is that okay, the 3GPP is when it transmits the reservation signal, it's do like some cheating or something bad things. Okay, maybe we can ask 3GPP to implement the SCR slot to be more fair and to be more cooperative. So if we imagine the situation that the 3GPP will stand at this at their point and saying that we are okay with the reservation signal, maybe Wi-Fi can propose something to protect itself from these reservation signals, for example, to understand that reservation signal is happening and, for example, not increment back-off counter for RTS, CTS or something like that. So maybe there is an opportunity to think on how Wi-Fi can protect itself from such reservation signals. So this is just a comment or maybe proposal for future.
Yeah, I believe that some methods can be designed from the Wi-Fi side, but you know, since the reservation signal is not defined in the specification, so it's very hard. I believe it will be very hard to for Wi-Fi stations to distinguish between reservation signal and some other signal, data signal, for example, from cellular networks or some other networks which can use this spectrum. So I believe that some methods can be designed, but it's not a very simple question.
Okay, yeah, thank you. Thank you.
Mikhail?
May I yet ask the question? Yes. Yeah. So my question is about the NRU, or let's say future NRU of some kind. So as all we know, the 5G introduces the flexible numerology and all those beautiful options to shorten the transmission slots and etc. And won't it actually help the NRU stations to find the transmission opportunities without reservation signals? Did you study these options and these possibilities?
Yeah, we have studied. In our paper, we studied the case, what will happen if we use the proposed method and decrease period of license slots. And what we have that when we decrease license spectrum slots, we decrease overhead. In fact, this leads to, when the baseline solution is used, this slightly increases the throughput of cellular networks, but and it also slightly increases the probability of asymmetric collisions if Wi-Fi net throughput is used, or Wi-Fi if RTS-CTS is used in Wi-Fi. But in fact, the better performance, according to our experiments, is just to use the same license spectrum slot as in LTE, so it's when it's quite big, but use collision resolution method which we propose.
And what if not using reservation signal at all? Will the degradation for the NRU will still be extremely high, let's say, or prohibitively high?
In fact, we have a number of papers on this topic. For example, the one I have cited here. So the main conclusion is that to fairly coexist with Wi-Fi, so to have approximately equal throughput or something like that, even if we take into account that the transmission duration of LTE or cellular network is higher than the transmission duration of Wi-Fi, we need to have license spectrum slot of about, it's dependent on the number of active stations, but it's should be very short, something like I guess 20 or 40 microseconds. So it should be very, very short. And when we have so short slots in the unlicensed spectrum, it significantly complicates the design of user equipment, because in comparison to Wi-Fi, where the transmission starts from preamble and it can be easily detected, cellular transmissions in unlicensed spectrum doesn't have some preamble. So user equipment should try to detect signal in every slot. So when you increase, when you decrease the duration of slot, you increase the complexity of user equipment. So in fact, let me summarize that if we decrease period of slots, it will help, but the price will be notable from the UE side at least.
And maybe it will increase the control traffic flow for in the downlink. Yeah.
Also
okay.
Control traffic. So quite a lot of issues.
Okay. Thank you.
So I guess Mikhail was the last who sent a question in the chat. So
do you have any other questions?
Sorry, just maybe not the question, but the ask maybe from my side, but maybe interesting for the whole group, for the whole our group, if there will be some decisions about Wi-Fi and LTE cooperation So whether to use or not to use reservation signals or some other methods, it would be interesting for me to just to look if such decision occurred, just to maybe to spread out this information for the whole group.
Okay. So any other remarks?
So, as I understood from our discussions, that there is no currently there is no consensus or solution between 3GPP and IEEE about how they will coexist, right?
Yeah.
So the discussion is still continuing, right?
Yeah.
Okay, thank you.
Okay, any other comments or questions? No comments, no questions. So that's all for today. Thank you very much for participation. Thank you, Vyacheslav, for presenting the results. And next time we will have the seminar next week, the same time, and I will present to you. I will make a talk on recent activities in 822.11. So that's all for today. Thank you. Have a nice evening. Goodbye.
Thank you. Goodbye.